let's talk about Carnot maps, or for short, KMaps. So KMaps are a graphical way of applying the combining theorem. And so recall from Boolean algebra that Boolean expressions can be minimized by combining terms. And again, our KMaps are going to do this graphically. So here's a KMap. This is our KMap down here. And it's going to graphically represent our truth table and allow us to combine terms. So the 0, 0, 0 row, so this row here, maps to this 0, 0, 0 box. The next location, 0, 0, 1, maps to the 0, 0, 1 box. So you can see that we have A and B input variables on the top kind of row here, and C on the vertical. And so we have each possible combination 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And then, strangely, we kind of jump over and do 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Well, why is that? Remember, combining, in order to use combining, our terms can differ only in a single term. And so you'll notice going to adjacent squares, these differ only in a single term. Going from top to bottom, they differ in the C term only, right? So going from here to here, A bar, B bar stays the same, only C, the C term differs. From here to here, A bar, B stays the same, and only C differs, and so forth, going from, one adjacent square from top to bottom. And you'll also notice going from, adjacently here, right to left, these differ in only B. Right? We have A bar, C bar. Those are the same for those adjacent squares, and they only differ in C. And likewise here, they differ only in A, and likewise here, differ only in B. If instead we had gone, right, 1, 0, 1, 1, like in counting order, now going from adjacent squares, these would differ in both the A term and the B term. And we want to be able to combine adjacent squares, and so that wouldn't work. Okay, so we enter our KMap by starting with the first row in our truth table. Goes into the 0, 0, 0 box. The next row, the 0, 0, 1, goes into our 0, 0, 1 box. 0, 1, 0 goes into the 0, 1, 0 box. 0, 1, 1 goes into the 0, 1, 1 box. And now, after we get to this point, we're going to jump over a column and go to the 1, 0 column. So we can get 1, 0, 0. So I'm going to go into the 1, 0, 0 box. And then 1, 0, 1 goes into the 1, 0, 1 box. And now we go back over to our 1, 1 column. Okay, so now we're at this row. And we'll get our 0 and our final 0 in the bottom row. So now that we've entered that our KMap, now we can circle adjacent ones. So here we have two ones that are together, so we can circle them. And we notice that, well, in our, this is just for illustration, don't need to, typically you won't use this, but we can see that those adjacent ones indicate A bar, B bar, C bar, or, right, these are our minterms, or A bar, B bar, C. And we know using combining that that is just going to be A bar, B bar. But we can do this graphically and see, okay, well, the C term has a true and complement form already included in that circle, so we're not going to include the C term in that implicant, in that product term. We're only going to include whatever terms only have one form of that variable in it. So A has the bar form of A in that circle, and B has the barred form, or complement form of b. So y is equal to a bar, b bar. But we can do this graphically now. It's a lot easier to see graphically than by performing Boolean algebra. In this case, either would be pretty simple. But as it gets more complex, KMaps become more useful. And so we have our, again, this was what, it's effectively what we're doing graphically is y equals a bar, b bar, c bar, or a bar, b bar, c. So we're going to circle ones in adjacent squares and include the literals whose true and complement form are not in the circle. So in other words, we're not going to include literals that have the true and complement form included in the circle. So y equals a bar and b bar. So here's another truth table and KMap, and we're going to enter in our ones and zeros into our KMap. So 0, 0, that's these top two zeros here. And we get a 1, 0, 1, 0 box. And our 1. Now we jump over a column. We get our 0, 0. That's going to be these two zeros here. And then jump back to the 1, 1 column. Okay, here's our 1, 1 column to get those last two outputs, 0, 1. Okay, so now we have our KMap completed, and we want to circle adjacent ones. So we can circle those two ones. And now it's tempting just to do that, right? It's tempting to just say, okay, well, I guess there's one left. But what we can actually do is we can enlarge the circle, make the circle larger here to get both of those ones. And that's effectively, right, our min terms here are a bar, b, c bar, a bar, b, c. And so we can clearly combine those two terms. They are the same in a bar, b, differ only in c. And here we have a, b, c. So we're effectively reusing that term. We're duplicating that a bar, b, c term. So we can reuse it, a bar, b, c term, so we can reuse it again in combining those with the last min term. And so we look at this circle up here, the red circle, and both forms of c are included, so we're not going to include c in our implicant, our implicant there, our product term, but only the false form of a is included, so we have a bar, and the true form of b, a bar b. And the green circle, well, both forms of a are included in that circle, the true and complement form. So a is not included in our implicant, but the true form of b is the only form that's included in the circle, in this green circle down here. So we have b and only the true form of c. And now we OR those implicants together and get a bar b or b and c. Or b and c. So let's go back to the definitions we introduced earlier. Remember, a complement is a variable with a bar over it. Literal is a variable or its complement. And an implicant is a product or an AND term of literals. Now let's introduce this last term. Prime implicant is an implicant that corresponds to the largest circle in a KMap. So implicants are any product of literals. A prime implicant is it corresponds to the largest circle in a KMap, or an implicant with the fewest terms. So let's talk about our KMap rules as we move forward. So every one must be circled at least once, right? Each min term has to be included in the function. Each circle must span a power of 2. So I can't, for example, circle 3 ones, but I can circle 4, right? I can circle 1 1, 2 ones, 4 ones, 8 ones, 16 ones, and each circle must be as large as possible. That will make the implicant smaller. And a circle may actually wrap around the edges as well. So let's look at this KMap that has 4 inputs. So we'll start with the truth table, and we'll start with these first 4 rows. So we enter our first row in our truth table. Here we get a 1, we get a 0, 1 and 0. And now we're going to enter into our output into the 0, 0, 1, 0 block, which is 0, 0, 1, 0. We have to skip a row and enter it into the bottom row. So this 1 goes into this bottom row, and then our last one for that group of 4 goes into the 0, 0, 1, 1 box. And again, we do that for adjacency. And now our next group of 4, we get 0, 1, skip a row, 1, here's our 1, 1. And now for this next group of 4, we need to jump over a column. We're going to start with the 1, 0, right? 1, 0, 0, 0 box. And so we jump over here, we get a 1, and then another 1, and skip a row, 1, there's our 1 here, and 0. And finally, our last group of 4, come back to the 1, 1 column in A and B, and we get 0, 0, skip a row, 0, 0. Okay, so now we filled out our KMap correctly. That's a common error, so be careful when filling out your KMap. And now we're going to find groups of 1s, so powers of 2 groups of 1s. And notice that our KMap actually wraps around from right to left, so we have this 1, 0, 0, 0 box, so A, B bar, C bar, D bar box. And if we go to the right adjacently, we see the 0, 0, 0, 0 box. And so those only differ, these 2 boxes actually only differ in A. So they are adjacent in that we can combine them, right? And so, same thing as top to bottom. So here we have our 0, 0, 1, 0 box, and here we have our 0, 0, 0, 0 box. These 2 boxes only differ in C. And so we could, we could combine those boxes as well. Okay, so the first thing to do in a KMap is to look for kind of lone ones that only have a single option for a circle. So this one here, we can't circle anything up or to the left or to the right. So it's kind of isolated. The only direction we can go is down. And so we can circle those 2 1s. Remember, we have to have our circles include powers of 2 groups of 1s. So it's tempting, people want to do this, but we can't, right? Combining works on pairs of things of terms that differ in a single term. So that would be wrong. Don't do it. But we can circle these 2 1s. Okay, and now we can look at any other ones that are kind of isolated. This one here can't go left, can't go right. Right to the right of that is that 0. Can't go down. So there's only one option for circling this one, and it is up. Okay, so we have those ones. Let's look for some other options here. So this one here can't go to the right, Can't go down because there's a 0 there. But we could go to the left and up. So we could go this way and we could go that way. And if we can go 2 directions, left and up in this case, we try to go left and try to go both directions, left and up. In this case we can because there's this 1 here. And so we can actually make that circle bigger into a circle of 4, right? A size 4 implicant, because it's circling 4 of these min terms, or these 4 ones. And so now we see what we have left. So what we have left here is this one and that one. Okay, so I'm gonna I'm actually gonna show a slight error here, and then show how to fix it. But so let's suppose we look at these and we say, well, let's see, this one down here, I could go to the right, or I could go down. Okay, so let's say we see this right one, and so we do this. And same thing here, we see on this one that we could go left, or we actually could go up, but we choose this one. And so this is, again, a slight error on this. But now we can draw our what our implicants are. So we have our red kind of circle here. It has the complement form of A, so we get A bar and B. Has the true and complement form of C, so we don't include that in our equation, but it has only the true form of D. Okay, so we get A bar, B, and D for that term. And now we have this green square here. This has the true and complement form of B, so we don't include that in our equation, but only the complement form of A. So we get A bar. And it has only the true form of C, but the true and complement form of D, so we don't include D in our implicant. Okay, and now let's do this blue term here. Has the true form of A, the complement form of B, so true form of A, complement form of B. And it has the true and complement form of D, so we don't include that, but only the complement form of C. Okay, so we have the blue circle covered. And now let's see the purple circles. So this top one is, well, let's see, it has the true and complement form of A, so we're not going to include that in our equation. Only the complement form of B. We have B bar and complement forms of C and D. B bar, C bar, D bar. And this bottom one has the true and complement form of A. So again, not going to include that. Complement form of B, C, and D bar. True form of C, complement form of D. Okay, so we put all of those in, and now we can OR these terms together, and we would get y equals, well, A bar C, this term, or A bar B D, or A B bar C bar, or B bar, C bar, D bar, or this last term, B bar, C, D bar. And so you may notice, well, wait, these terms I could have combined. B bar, C bar, D bar, B bar, C, D bar. There's only different in the C term. So I could actually combine those two terms and get just B bar, D bar. And so that means if I can combine terms after I've completed my KMap and written them into my equation, it means that my circles are not big enough. So in this case, actually, it turns out that we could have included all of these ones in the corners into a single large circle. And so we could have, we have ones in the corner. It turns out those are, well, the true and complement form of A is in the circle, so we don't include that. Only the complement form of B is in that circle. True and complement forms of C are in that circle, but only the complement forms of D are in that circle. So the 4 ones in the corner are B bar, D bar. And here we show those correct circles and the equation A bar C or A bar B D or A B bar C bar, and then our final value, this circle of 4, right? This size 4 implicant because it has 4 min terms included in it. This is our B bar D bar implicant.